Welcome back to math. This is section 13, where we're going to talk about probabilities, combinations, and permutations. We'll cover simple probability, compound probability, the fundamental counting principle, and of course combinations and permutations. Probability predicts how likely an event is. Simple probability means we're predicting the chances of just a single event. Probabilities are often given in percent format, but they can also be given as a fraction, decimal, or even a ratio. If something has a 100% probability, it will certainly happen. If it has a 0% probability, it will definitely not happen. The formula for simple probability is the number of successful outcomes divided by the total number of possible outcomes. Let's do an example. Imagine we want to find the probability of tossing a coin one time and getting heads. There are a total of two possible outcomes, right? Heads and tails. Success for us, the one we want, is heads, and that's only one of those. So the probability is 1 divided by 2, or converted to a percent, that's 50%. As another example, suppose we choose one card from a deck of cards, and we want to know the probability that it will be a diamond. So now there are 52 possible outcomes because there are 52 cards in the deck. And we're looking for diamonds. There are 13 diamonds in the deck. So that makes 13 successful outcomes. 13 divided by 52, that's 1 out of 4, or as a percent, that's 25%. There's a difference between the simple theoretical probability that we're calculating here and experimental or empirical probability. In theoretical probability, we are predicting what should happen. In experimental probability, we're actually performing the event and recording what happens. So for example, suppose we toss a coin 10 times. Theoretically, it should land on heads exactly 5 times and on tails exactly 5 times. But in reality, the coin might land on heads 6 times and on tails 4 times. The more times that we toss that coin, however, the closer the experimental probability will get to the theoretical results. So now let's talk about compound probability. It's the probability of 2 or more events, and it's different than simple probability in 2 ways. First, there's the issue of dependency. Independent events do not affect each other. Examples of independent events are like tossing 2 coins, throwing 2 dice, or drawing a card from each of 2 different decks of cards. In these examples, the probability of the second event won't change just because the first event happened. But dependent events do affect the outcomes of each other. An example of this is drawing a card from a deck and then drawing another card from the same deck without replacing the first card. The probability of selecting the Queen of Hearts as your first card is 1 out of 52. There's 1 Queen of Hearts out of 52 cards. But if you draw a card and don't get the Queen of Hearts, and you draw again, now your successful card is still 1, but there's only 51 possible outcomes left. The second way that compound probability is different than simple is we can distinguish between event 1 and event 2 happening, in which case we multiply together their probabilities, and we can also calculate the probability that event 1 or event 2 would happen, and in that case we add their probabilities, but we have to remove some overlap. Again, let's do some examples. Let's find the probability of 2 events. They're both coin tosses, and we want to know the probability that we would get heads on both the first toss and the second toss. These are independent events. That's because the probability won't change for the second coin toss just because the first toss occurred. The probability of heads on the first toss is still 1 out of 2. There's still 2 possibilities, heads and tails, and heads is one of those. The probability of getting heads on their second toss is still 1 out of 2. 1 successful event of heads out of 2 possibles, heads and tails. So to find the probability of getting heads on the first and the second toss, we're going to multiply those two together. And of course we get 1/4, or 25%. Here's another way to think about that. You could have, on your first and your second toss, you could get heads and then heads, or heads and then tails. You could get tails and then heads, or you could get tails and then tails. Those are the 4 possibilities of what could happen. But we're only talking about heads and heads, and that's 1 out of the 4 possibilities. Here's another compound probability example with an event 1 and an event 2. We're going to pull some marbles out of a bag without replacing them. And this bag has 6 blue marbles, 3 red marbles, and 3 green marbles. We want to know the probability of choosing 2 red marbles without replacement. So because this is without replacement, this means that they are dependent events. That means that the probability of the second pull will change based on what we pulled the first time. So the probability of getting a red marble on the first pull is, there are 3 reds, so there's 3 chances of success, and there are 12, 6 plus 3 plus 3, total of 12 marbles. But now, and you have to assume that the first marble was red, or we wouldn't continue. It wouldn't make any sense. If the first one's not red, we certainly can't pull 2 red marbles. So the second time we pull marbles out of the bag, there's only going to be 2 red marbles left, and 11 total left. So the probability that the first and second will be red is 3/12 times 2 11ths. And that is 6 out of 132, or converted to a percent, it's 4.5%. Here's a compound probability example where we're looking for event 1 or event 2 to happen. We're going to draw 1 card out of a deck, and we want to know the probability that the card is either a 4 or a 7. And we're going to use replacement. It means we're going to put the cards back the first time. That means these are going to be independent events, and the probabilities won't change between the two. So one of our draws, it doesn't matter whether it's the first or the second, but the probability that one of our draws is a 4. So there are 4 4s in a deck of cards out of 52 possibles. We put the cards back between draws, so there are 4 7s out of a deck of 52. So when we're doing an OR event, we add them together. 4 52 plus 4 52s equals 8 52s. And again, converting that to a percent, we'd get 15.4%. We don't have to eliminate any overlap because there are no 4s that are also 7s. Here's another example of a compound probability with 2 events. We're going to draw 2 cards out of a deck, and we want to know if event 1 or event 2 could happen. So we want to know the probability of drawing a 7 or a heart, and again there's replacement, so these are independent events. So one draw, doesn't matter again whether it's the first or the second, but being a 7, there are 4 7s out of the deck of 52. With the cards replaced, this is an independent event. It doesn't matter what happened the first time. Drawing a heart, there are 13 hearts out of 52. But now we do have to consider that there's overlap because there is the 7 of hearts, and we can't count that twice. So the 7 of hearts is 1 card out of the 52. So the probability of drawing a 7 or a heart in 2 draws is 4 out of 52 plus 13 out of 52 minus that overlap. So that actually is 16 out of 52. Or converted to percentages, that is 30.8%. There are many different ways to select and arrange objects, and first we're going to talk about the fundamental or basic counting principle. And this says that if you have item A that has A number of possible outcomes, and an item B that has B number of possible outcomes, that there are A times B number of possible arrangements of those two items. So here's an example. Imagine that we're going to a restaurant, and there are 5 different appetizers we could choose, 8 different main courses, and 3 different desserts. We want to know how many different meals we could choose. You have to assume that we're going to choose one thing from each category. So there are 5 times 8 times 3 combinations. That's 120 different meal possibilities that we could have. Here's another example. Imagine you're selecting your PIN number and you get 4 digits. You can reuse the digits. You get to choose between 0 and 9 for each one. That's 10 different combinations. 10 possibilities for your first digit, times 10 possibilities for your second digit, times 10 for the third digit, times 10 for the fourth digit. That means 10 times 10 times 10 times 10, 4 zeros. There are 10,000 different combinations of PIN numbers, if you can reuse digits. Now let's talk about combinations. And combinations find how many possible outcomes could happen when you're selecting items from a set. In a combination, it's really important to remember that the order in which the items are selected does not matter. The formula for combinations is n factorial divided by k factorial times n minus k factorial, where n is the number of items and k is the number that we're going to select. I know that looks confusing, and obviously first of all we need to talk about what factorial means. This symbol, the exclamation mark, means factorial. We read this n factorial, and it means that we're going to multiply the number n, whatever that is, by itself minus 1, by itself minus 2, by itself minus 3, and on and on and on until we get down to the number 1. So 5 factorial we write as 5 with an exclamation mark. It's 5 itself times 5 minus 1, that's 4, times 5 minus 2, times 5 minus 3, and all the way down to 1. And when we do that all out, we get 120. Just notice that if you ever come across it, that 0 factorial equals 1. Now that we've talked about factorial, the combination formula won't look quite so difficult. So here's our example. We're at an ice cream shop, and they have 31 flavors of ice cream, and we get to choose 2. It doesn't matter to us which order we choose them in, as long as we get the 2 flavors that we want. So n is the number that we get to choose from. That's the 31 flavors of ice cream. And k is the number that we're going to choose. That's 2. We're going to choose 2 scoops of ice cream. So n factorial is 31 factorial, divided by k factorial with that still looks kind of confusing, but it's not. When we write this out, we don't have to write it out all the way. This is 31 times 30 times 29 factorial. I'm going to stop writing it out there. And this is 2 factorial times 29 factorial. Now, 29 factorial, it would take a long time to write that out, but it's a factor of both our numerator and our denominator. So we can actually cancel it out. That's 1 over 1 essentially, right? So 31 times 30 is 930. And of course 2 factorial is 2 times 1. That's just 2. So when we divide that out, we get 465. and we find that there are 465 different ways to combine 2 flavors of ice cream out of 31 things. Let's do another example of combinations like that. So this time we have an example where there are 2 class times on Saturday at your school. And there are 6 classes, and all 6 classes are taught both times. You want to take 2 classes. It doesn't matter whether you take the first class in the first period or the second period, you just want to get 2 classes. So how many different combinations of classes could you take? Alright, so n equals the number of classes that you have to choose from, that's 6. K is the number that you're going to choose, that's 2. So we'll replace this into our formula, that is 6 factorial divided by 2 factorial times 6 minus 2 factorial. That equals 6 factorial over 2 factorial is just 2 times 4 factorial. So when we write this out, we can stop writing out 6 factorial when we get to 4 factorial. I'll show you what I mean. It's 6 times 5 times 4 factorial over 2 times 4 factorial. I wrote it out that way so that I could see easily that this and this cancel out. 6 times 5 is 30 divided by 2, and that's 15. So there's 15 different ways I could choose 2 classes out of 6. Since there's only 15 combinations we can choose, let's write out what they are so we can really see how this works. So again, out of 6 classes, we can take 2, and the order does not matter. So we could take class 1 and 2, 1 and 3, 1 and 4, 1 and 5, 1 and 6. Now, taking class 2 and 1, that would really be the same. We've already counted that possibility. So we can take 2 and 3, 2 and 4, 2 and 5, 2 and 6. Or, here we keep going, 3, 4, 3, 5, 3, 6, and on until we see that there really are just 15 choices. Now let's think about permutations. And permutations are similar as combinations, but now the order does matter. There's really 2 permutation formulas that we're going to look at. The first one looks like this, and it tells us how many ways n things can be placed in n slots. That means that all the items are used up. So n things, putting them in n slots, can be done in n factorial different ways. Again, let's do an example. Here's an example of a permutation where all the slots are used up. So 5 people are going to get in line to give their book report. How many ways can they line up? First, second, third, fourth, and fifth. Again, they're all getting in line. So n is 5, and we say p equals n factorial. We already did this example, but n factorial is 5 times 4 times 3 times 2 times 1, and that in fact equals 120 different ways that these 5 people could line up in order to give their book report. Here's the second permutation formula that we're going to look at. And again, it's a permutation, so the order does matter. And in this formula, we're considering how many different ways n things can be placed in r slots. R is less than n, so that means that not all the items are going to be used. The formula has more factorials. We just need to know n and r. N is the number of things, and r is the number of slots they're going to be put into. Let's do an example. Here's our example for the permutations. 10 people are going to run in a race where the fastest 3 will get a prize, first, second, and third. So not everybody's going to get a prize. There's only 3 slots, in other words. So n is the number of people who are going to run the race, and r is the number of slots that they could get a prize for. We're going to write this as p, n is 10, r is 3. and we'll just substitute. So now 10 factorial over 10 minus 3 factorial. And again, let's write this 10 times 9 times 8 times 7 factorial. I stopped writing it there because 10 minus 3 is 7 factorial. So again, this and this cancel out, and 10 times 9 times 8 is 720. So that means there are 720 different permutations for how 10 runners can come in first, second, and third. Let's do one more example of that kind of permutation. So now we're going to look at a 4-digit pin that we can select. And again, we're going to use the digits 0 to 9, but we can't repeat the digits. So n is the number of digits that we can have. That's 10. R is that we can only choose 4 slots. So P 10 4 equals 10 factorial over 10 minus r factorial. It's 10 times 9 times 8 times 7 times 6. 10 minus r, r is 4 over 6 factorial. This cancels out, and we come up with 5,040 different pin numbers when we can't reuse numbers. There are some other great examples in the practice problems, so try to do those on your own, and then watch the video and we'll solve them together.